All right, so welcome everybody, either this morning or this afternoon. Let's get started again with a little warm-up question. So just like yesterday, I collected a couple of statements. They're related to material from just yesterday. And this time we're looking for a correct statement. So be prepared for a lot of nonsense. Statement A is charge dispersion is large in the transmon regime and small in the charging regime. B says, when approximating the cosine potential of the transmon by a parabola, the dependence of eigenenergies on the offset charge is irretrievably lost. C says, the larger the charge dispersion, the longer the expected pure dephasing time in the charge noise channel. And D says, the smaller the anomalisticity, the easier is it to keep the transmon confined to the 0,1 subspace. And let me just paste the link in the chat once more. Here it is. And I will monitor how many people are playing the game. One person. Still only one person. So we have 26 people online. And now we have 6. All right, I like that. Let's give you another moment to think. And now we have 7. This is growing very slowly. Can we get a couple more people to vote? You know, it's anonymous. I don't even know who. First of all, I don't know who you are, but I also don't get any IP addresses or names attached with votes. So there's no embarrassment. And having an opinion and committing to one, even if it's a guess, is sometimes a good idea. So let's see, what do we have now? 10. All right. Sure. I'll take 10, and the results are in. So let me shift that window over to where you can see it. So we have a mixture of things. There is, well, a slight majority for B, but it's not overwhelming. So let's talk about the individual choices and go through them one by one. So charge dispersion. Charge dispersion was, what was that anyways, right? It was, roughly speaking, how much do my energy levels vary as I change the offset charge? And in the transmon regime, this was sort of one important property of the transmon, those energy levels were fantastically flat. So the charge dispersion there is small, and it was actually large in the charging regime. B, I'll come back to B in a moment. Let's get over to C. The larger the charge dispersion, the longer the expected pure dephasing time. Not really, actually the opposite way, right? So we discussed that what is bad in terms of dephasing and actually makes the dephasing time short is if the energy levels fluctuate so that the qubit energy splitting varies. And if the charge dispersion is large, then there's a lot of variation and the pure dephasing time is going to be short, which is what we saw for the Cooper pair box, which is in the charging regime. And then D says the smaller the anomalisticity, the easier it is to keep the transmon confined to our computational subspace. Well, if the anomalisticity is small, then we're close to a harmonic oscillator. And the thing was, harmonic oscillator has all equidistant energy levels, everything is equally spaced. And so keeping the system in the lowest 2 energy levels is difficult. And if you just use coherent tones, it's impossible. So we want larger anomalisticity to make it easy to stay in the 0,1 subspace. So that leaves us with B. So B is the correct statement. And when you think about it, I hope you remember some of the things. It's a little bit surprising at first. So we make an approximation We're used to the fact that approximations are not perfect. That's why they're called approximations. But the effect of the offset charge really is completely lost when we go away from the cosine potential to the parabola. And I think I mentioned briefly that last time that the effect of the offset charge has to do with the fact that the particle can tunnel from one well to, well, actually the same well as it goes around the circle. And as soon as I replace the cosine by just the parabola, there's no more such tunneling. It's impossible. And if you're wondering how this works mathematically, you can try and perform a gauge transformation, which I think I didn't write down last time, but I can do that now if my pen would like to work. Yep. So you can define new wave functions. I call them psi bar of phi, and they're related to the old wave function psi of phi by a position-dependent phase factor. And whether you have to choose the plus or the minus depends on whether you had the plus or the minus ng in your Hamiltonian. And the effect of that is that once you figure out what is the new Hamiltonian that governs the Schrödinger equation for psi bar, that is independent of ng. So ng disappears from the Hamiltonian. If the boundary conditions are periodic, then this gauge transformation switches us from periodic boundary conditions to quasi-periodic boundary conditions. And the ng, the offset charge, reappears in the boundary conditions. But if we've made the approximation of replacing the cosine by a parabola, then the boundary conditions are just that the wave function has to vanish at plus minus infinity, and the ng truly disappears from the problem. So that's the story, part of the story at least behind that. Does that make sense, or are there questions about this? Okay, if there are no questions, then I had some doubts after finishing the lecture last time about two things, both of them minus signs. So I recall that I sort of started stuttering and stumbling when it came to assigning values of n to the charge parabola. And PowerPoint did not save my scribbling on the screen, so I actually cannot double check, but I suspect that I just did it wrong. So just so that we agree, right? If I have this expression n minus ng, and I set n to plus 1, then this is a parabola that is centered at ng equals plus 1, right? That's where this expression becomes 0. And I think I might have just gotten this exactly the wrong way around last time. And if so, I apologize. And then there's one more minus sign. If you're new to this, I tell all my beginning graduate students that if they really want to be theorists, they have to be prepared to search for minus signs for hours of their life. Probably when you die, you should put on your tombstone how many days you've lost by looking for factors of 2 pi and minus signs. So I'm not free from that. I did mumble something about a sign in front of this qubit term, the 1/2 h bar omega q times sigma z, and that is unfortunately a place where you basically can't do it completely right. Something is always going to be funny. And we'll just follow one convention. We'll pick the plus convention, which is the one also offered by Alexandre Blais in his review, but I'll quickly say what's up with that. So if you use the standard definitions for the Pauli matrices, like everybody does, then there's this interesting difference between sigma plus sigma minus, which we could sort of think of as the two-level version of A dagger A, and in many ways it is that. But it has different ordering, right? It actually has the 1 in the first position on the diagonal, whereas for A dagger A, the numbers increase as we go down the diagonal. So that's all right, and we can live with that. The thing that is really bothersome is if you look at any good old quantum computing textbook, here's the some people consider it the Bible, so Nielsen and Chuang, and the convention that everybody uses that I know of is that when you have a quantum state with computational state 0 and 1, then the alpha and beta coefficients get fed as components into this vector in this very order, right? Which means that the 1, 0 state is the 0 state. That's good. But if I use the plus sign in front of my Pauli term here in the Hamiltonian, then that happens to mean that the 0 state is the excited state, which is not what any experimentalist usually does. And so at some point, you will have to make a compromise and find your own way to deal with that. Since in my lectures, we're actually not talking too much about quantum computing at the level of performing gates, I'm going to ignore this little conundrum and will proceed with the plus sign as it is used in Alexandre's review. Good. So then let's pick up where we left off last time. So we wanted to talk about the Jaynes-Cummings model as a beautiful toy model that describes the interaction between matter and light. And here it is again, right? It describes a two-level system, or you can name it qubit. There's a harmonic degree of freedom. And then there's this simple form of interaction between the two subsystems that allows me to convert an excitation of one kind into the other kind. I mentioned last time that essentially this corresponds to infinite anharmonicity. If you're interested actually in a little bit of history of that, there are some articles, one actually from 2013 by Fred Cummings himself. Unfortunately, he passed away just about 2 years ago. And it's very fun to read. It's maybe a page, and he was a great person who was, some people who make a name of themselves are not very humble anymore towards the end of their lives, but he was very humble, and he described his achievements as a story of diagonalizing a 2x2 matrix. And of course, his story has something to do with that, but just read the article. It's really, really nice. All right. Now we're in the business of trying to understand the spectrum of this model. So here the two subsystems are represented with a little cartoon once again. And let's start thinking about how we would go about finding the eigenenergies and the eigenstates in this problem. And so what's pretty clear is that our Hilbert space is a tensor product of the Hilbert space for the R. I believe Alexandre chose because oftentimes the oscillator is a resonator. So this is the Hilbert space of the oscillator / resonator. And here's the qubit. And of course, we can simply define an orthonormal basis of the joint Hilbert space by taking together the Fock states indexed by n. Those span the oscillator subspace. And then for the qubit, I'll interchangeably use G and E for ground and excited state, and in some places 0 and 1, because counting is more fun with numbers than with letters. And one quantity that is super useful to consider in this context is this capital N. What is it? Well, A dagger A counts the number of excitations in the oscillator, and sigma plus sigma minus counts the number of excitations in the qubit, which can be 0 or 1. And so when I add up these two, I get the total excitation number. And it's an observable, and we'll see in a moment why this observable is so important. What's easy to understand is that our simple basis states, bare product states of Fock state in the oscillator and one of the qubit eigenstates, those are already eigenstates of the total excitation number, right? All I need to do is I need to look up, well, what is n, what is sigma, here interpreted as 0 and 1, and I add up those two numbers. That is the total excitation number. And we can say this in a little bit more detail. So eigenvalues are the integers starting at 0. And 0 is special because there's only one guy that leads to eigenvalue 0, namely no photon or no excitation in the oscillator and qubit in the ground state. So that is non-degenerate. And then all the higher eigenvalues follow a pattern where it's a pair of these Bayer product states that lead to that particular eigenvalue. So this here is the single excitation subspace where the excitation can be in the oscillator, or it can be in the qubit. So both of them have eigenvalue 1, and then likewise here it's for 2 in the oscillator, or 1 in the oscillator, 1 in the qubit, and this pattern just continues, you can easily imagine. And so why is this helpful? Let's play a little game and see what happens when we apply this total excitation number operator from the left to our Hamiltonian. So I've just written this down, and we're going to ponder without actually algebraically evaluating commutators. We'll sort of in a hand-wavy but intuitive way determine whether or not I can move that n over to the right. So the sigma z basically is as good as counting the number of excitations in the qubit with a shift of sorts, but it certainly doesn't change the number of excitations. So that n I can move to the right. That's good. And then this guy over here, right? That should do something very similar because a dagger a doesn't change any excitation number, so n can be moved over to the right. And now comes the interesting part, which is the interaction term. We mentioned, right, that this has the form that basically just involves conversion of an excitation, right? I can take an excitation from the oscillator, that's what A does, and convert it into an excitation of the qubit. That doesn't change the total number of excitations. The same goes for the second term. And so I can move n across, which means that n and the Hamiltonian commute. And that, of course, tells us that the total excitation number is conserved, which oftentimes is a very nice thing to know because it can help us simplify the task of finding eigenenergies and eigenstates of the Hamiltonian itself. Right, the statement that you should have heard in a good quantum mechanics class is that if you have such an observable, it commutes with the Hamiltonian, then you can construct an eigenbasis that diagonalizes n and the Hamiltonian simultaneously. Now, we're in the situation where n has some degenerate eigenvalue, so we have to be a little bit careful, but it's not bad because the degeneracy is just a maximum of twofold. And so the simplest guy to take care of immediately, right, is the ground state that is non-degenerate. It's an eigenstate of n, hence it has to be an eigenstate of h. And you can try, right? We can apply the Jaynes-Cummings Hamiltonian to the state. Sigma z is not going to change anything. A dagger a is not going to change anything. Where by change anything, I mean you can throw out a constant prefactor, but the state itself does not change. And then, well, the interaction, what can it do? This term here involving a applied to 0, the 0 Fock state is going to kill this state. And similarly here, the sigma minus is going to find that the qubit is in the ground state, and then that state gets killed as well. So indeed, we find that our ground state is 0g, and it has eigenenergy -1/2 h bar omega q. Good. I hope so far so good. And then for each of the other subspaces, everything just boils down to the 2x2 problem that Fred Cummings talks about, right? I know that these two guys have the same eigenvalue of n, so I must be able to rotate within that two-dimensional subspace and turn those two also into eigenstates of our Hamiltonian. And so the simple idea is, let's write down these 2x2 matrices where I've sketched out what that means, right? We take the two partners within the n excitation subspace, we calculate the matrix elements, and then once that is done, all we have to do is diagonalize a 2x2 matrix. So, oops, I don't know what that was about. So let's do that. calculating the matrix elements, well, I can briefly outline how I would go about that, right? So we could start with this top left matrix element. I'm going to take my state ng, and so if the qubit is in G, then sigma z is going to be -1, so I'll get a minus omega q over 2, and then for this next one here, I have to count how many photons are in this state, so that throws out a factor of n. And then since this is a diagonal matrix element with the same state on the left and right, this interaction term doesn't give a contribution. The interaction does give a contribution in those off-diagonal elements, and I hope you'll be able to check in your own time that indeed these are the right results. So the matrix that we have to deal with looks just like that. It's a 2x2 matrix, and everybody can diagonalize a 2x2 matrix, but we'll do that together for an important and special case, namely the one where the oscillator and the qubit have the same frequency. You can call that the resonant case, right? Omega r is the same as omega q. And in that case, the two diagonal elements become the same. So that makes diagonalizing that matrix even simpler. The kind of matrix that we have is of this form. It's A, B, B, A. And I do hope that you'll be able to find that the eigenvalues are of this simple form, where the vectors are basically they're the symmetric and antisymmetric combinations of the vectors 1, 0, and 0, 1. And for us, that means that we have superpositions of the two partners in each total excitation subspace, right? So we have the guy that has n photons, but qubit in the ground state. We have the partner that has 1 photon less, but the qubit in the excited state. And well, this is now a superposition of this excitation being shared between the oscillator and the qubit, or if you wish, between light and matter. And some people lovingly call this the qton and the phobit, because the two subsystems are hybridized and you can't really say which one carries the additional excitation. And the corresponding eigenenergies look like this. So what's interesting about this expression is that there is this square root of n, right? So if we look at the spectrum, which I think is coming up next, we'll see that the square root plays an important role. So let's see, the way this is organized is as follows. All of these are eigenenergies of our bare system. So if I switch off the interaction and the systems are on resonance, then here's the bare product state, no photon, qubit in the ground state. Here's the first state in the single excitation subspace where I have 1 photon. And since we're in resonance, that's just as good in energy value as having the excitation sitting in the qubit. And so you see on resonance, every energy above the ground state is doubly degenerate. And that degeneracy is being lifted by the coupling. And so we get this wonderful ladder where I'm going to try and draw this a little bit so that it's clear. So this one continues here and those two split up, right? And of course, we're sort of used to the fact that if I had two harmonic oscillators that I coupled together, I can also get avoided crossings, no problem, right? I'll get new mode frequencies. There will be some splitting, but what's special about the Jaynes-Cummings model is that that splitting actually varies from the single to the 2 excitation subspace to the 3 excitation subspace, right? Because this here, what is this splitting? Well, that splitting should just be 2 h bar g, right? So I have the plus and minus with n equals 1, so that seems all right. And then, well, what's the next one? The next one is going to be plus or minus root 2 h bar g, so that splitting now differs by a factor of root 2. And I guess the 2 is still up front, h bar g. doesn't look very nice, but there we go, right? And so this square root of n, that is something that, historically people that wanted to demonstrate the James-Cummings physics for the first time, perhaps using actually cavity QED experiments, this square root of n was a smoking gun that people were hunting after, so that they could be sure that they had demonstrated this James-Cummings physics. All right. Now, the resonant case, of course, is only a very special case. So we could ask, well, what happens in general? Can we just agree on what the result is? And I do encourage you to go through this exercise, but I will record the result here. It's useful to introduce the parameter delta, which is the frequency difference between qubit and resonator, oftentimes called the detuning. And so with that parameter, we can write our 2x2 matrix in this form, which abbreviated, right, has this form. It's A minus B over 2 C A plus B over 2. And this is really a nice exercise. Just check whether you still remember how to diagonalize 2x2 matrices. And if you parameterize your result in a smart way, where you from the beginning on, you'll name this coefficient in front of each of these states. You'll use cosine and sine of an angle over 2. Then this takes a fairly compact form. This angle theta involves an arctan, you'll find out. And the eigenenergies now look just a little bit more complicated with the typical square root that we kind of expect when we find the roots of a characteristic polynomial that is of second order. There is, I did contact Alexandre this morning, and he didn't want to say yes or no yet, but I suspect that there could be a small typo in one of the equations in the review. They shift the spectrum, which would perhaps lead to this 1/2 or minus 1/2 going away, but then they seem to write down the ground state unshifted. So it could be that there's a small typo, and maybe this is a good challenge for you to actually determine whether or not they're right or I'm right. Somebody's got to be wrong. All right. Now, this is general James-Cummings spectrum. It looks a little bit abstract. The regime that is of huge importance in the context of superconducting qubits and resonators is called the dispersive regime. And well, I can say a few words about what that is supposed to be and mean before we jump into the math. So oftentimes when we want to operate on qubits, we're interested in the qubit not being strongly hybridized with the oscillator, right? The oscillator is there so that we can feed in photons, that we can do readout, but in most cases, we want to be able to say the state of the qubit is XYZ, right? And so that would imply that there's not strong hybridization between qubit and oscillator as it would be in the case of the resonant configuration. And so dispersive means that we want, well, in some sense, we want the interaction to be small, and we'll have to discuss what that is supposed to mean, right? So the interaction is here. And of course, small interaction, if something is small, I have to compare with something, right? G actually has units, H bar G is an energy. So what is small supposed to mean? What is the dimensionless parameter? And there are different ways to think about this. Since we already have the exact solution here on the slide, we can actually just do one simple step of manipulation. I'll take a look at the square root, which is the term that involves the coupling. I'll drag out the delta squared in front, and I actually get a square root of 1 plus some parameter, which involves the coupling strength, right? And so small coupling, that might mean that I'm looking at a situation where this parameter is small-ish, whatever precisely that means, and where we find convergence, we could discuss, but we want that parameter to be small. So in a little bit more detail, right, if I take the square root, then that means I might demand that 2g divided by the detuning times the square root of n is small compared to 1. Oversimplified, when people kind of think about just the single excitation subspace, you'll find people to just set n to 1, and they will say that g, the coupling strength, has to be small compared to the detuning delta. In principle, I might, to be extra safe, I should put an absolute value sign around that delta as well, because depending on whether the qubit is above the resonator frequency or below, this delta can be negative, but we'll imagine the absolute value sign there. Okay, and then on the other hand, suppose that you're given some g over delta. We can ask, well, at what photon number does this perturbation theory break down? When can we be sure that this dispersive regime is not valid anymore? And so I can do the simple-minded thing and just set this parameter to 1, and I get the result that the critical photon number, where clearly all perturbative approaches for this are going to fail, that critical photon number is delta over 2g squared. All right, so we've learned a little bit, and now the question is, how can we simplify this problem? Different ways. We want to do perturbation theory in this parameter, assuming that it's small. And of course, you can do good old stationary perturbation theory, which will tell you about corrections to energies and to states. Since we're in this wonderful position of knowing the exact solution, you could just as well take that exact solution and directly do a Taylor expansion of that. That's a luxury that we typically don't have, but since this model is exactly solvable, we can do that. And then there is an alternative which is more tedious, but for practical purposes, it's super helpful. And that goes under various names. I'll call it Schrieffer-Wolff transformation. Some people call it adiabatic elimination. Maybe there are other names as well. And let me just describe what the idea is. At the very heart, this transformation is doing perturbation theory. And so when we do ordinary perturbation theory, as I said, we calculate corrections to eigenstates, which basically corresponds to a rotation or a unitary transform that we act upon the unperturbed states. So I'll call that an active rotation. What Schrieffer-Wolff transformation does is it does a passive rotation. So instead of applying the rotation to the eigenstates, we're going to rotate the Hamiltonian. So we'll apply that unitary transform to the unperturbed Hamiltonian and get a new and simplified effective Hamiltonian in which this interaction is eliminated up to some given order. As I said, this procedure is a little bit tedious, and Alexandre has a long appendix in his review. I think a nice place also to learn about this systematically is this is a little chapter at the end of chapter 1 in this book called Atom-Photon Interactions. So if you've never heard about this transformation, then I would encourage you to read a little bit there. And obviously, if you have questions, you can still ask me. I'm giving another short lecture on Monday, and I'll be around. Good. So if you follow that strategy, if you perform the Schrieffer-Wolff transformation up to second order, you go from the original Jaynes-Cummings Hamiltonian up here that involves this coupling term to a new Hamiltonian that, well, it still contains our oscillator part. That's good. Here's our qubit. And that qubit now has a perturbative frequency shift that comes with g squared over delta. Oh, and I think I'm missing, if I want to keep track of h bars, then one would be missing there, for instance, probably, yeah. And so that's there. Some people call it Lamb shift because this qubit is a little bit like an atom that is coupled to the electromagnetic field. And so we get a shift of that atom frequency due to its coupling to the field. And then the last term is a very important term. It has a structure that combines sigma z with a dagger a. So it counts the number of photons, multiplies that with the Pauli z, and the coefficient h bar chi is also known as the AC Stark shift. And let's see, I did want to say something about what, how do we interpret that term? There's actually two interesting interpretations that are useful to consider. In the first one, I'm going to just algebraically rewrite this. Nothing big. I'm just going to pair this this particular term with the term for the oscillator. And so if I read this particular form, then I would say, well, it looks like the frequency of my oscillator gets shifted by an amount that depends on the state of the qubit, right? So if the qubit happens to be in the +1 eigenstate of sigma z, then I get a plus h bar chi shift. If it happens to be in the -1 eigenstate, then the shift goes in the opposite direction. And this shift, this qubit state-dependent shift of the resonator frequency is the core idea of how dispersive qubit readout works. And my understanding is that the plan is that Alexandre will talk more about this in his lectures. There's an alternative pairing of this AC Stark shift term. This time I'll group it with my qubit term, and I think I made a typo here. Yeah, that happens when we do a lot of copy and paste. So the coefficient here is clearly wrong, right? So we'll write this as, yes, I have to put it 2 chi here for now. So right, this now looks as if the qubit frequency gets shifted by an amount that actually depends on how many photons are inside the cavity, right? So if no photon is in the cavity, then the qubit frequency is whatever it wanted to be, including the Lamb shift. And if there's a photon, then it gets shifted by a certain amount. So the coefficient here being 2 chi. And that has been seen in experiments as an effect that it's in two-tone spectroscopy that you would find that, and it's called number splitting. The qubit frequency is actually split into multiple peaks that depend on the content, the photon content of the resonator. Good. Any questions about this? I'm going faster than I thought I would, which is not a bad thing per se, but it could mean that I'm going so fast that I'm losing people. So I would encourage you, if there are questions or some need for clarification, this would be a good point before I just go full steam ahead and continue. I always wish that Galileo Galilei would ask a question, but he's the most silent on Zoom. All right, no questions. So then this was the Jaynes-Cummings spectrum, but really we were interested in a model that was slightly more complicated and also lived in an opposite limit as far as the anharmonicity was concerned, right? So we would like to go back from the Jaynes-Cummings model to our system of transmon and oscillator. That's what we're really interested in. And here, just to show you the contrast, once again, this is what we just discussed, right? The two-level system coupled to oscillator with infinite anharmonicity. And then we want to go back to our transmon, here already approximated as this weakly anharmonic oscillator. It's a multi-level system, and that multi-level system couples to an actual harmonic oscillator. And then there's the sort of coupling here that kind of mimics what we have up there, except for now both subsystems are multi-level systems. Okay. Now.
There was a question, Jens, before.
Oh, perfect. Oh, I'm so sorry that I overlooked that. Has all this procedure been done for a pair of interacting transmons? Where Tommaso, since I don't know when you ask this, when you say this procedure, you mean what we discussed for the Jaynes-Cummings model? Tommaso is frantically typing. The Schrieffer-Wolff transformation. Thank you. So we applied, so far the Schrieffer-Wolff transformation that I talked about was really applied to Jaynes-Cummings, meaning we had a strict two-level system, idealized two-level system, no other levels, coupled to one oscillator. So that system in many ways looks a bit different than two transmons, right? Two transmons, what would two transmons be? I could modify the Hamiltonian that we have up here, right? I could insert yet another term here where maybe the A oscillator now gets a similar nonlinearity. That could mean that this oscillator is also a transmon, in fact, right? And then we could talk about that. But that is not what I've done so far. It's also not what I had in mind, even though the question is an interesting one. You can couple two transmons to each other directly or indirectly. I think you can couple them directly by capacitor. That would be charge coupling. Or you can place two transmons inside the same resonator. In that case, they undergo an interaction that is mediated by the resonator. If I reduce it again to two levels, it's sort of a flip-flop interaction where one qubit can emit an excitation into a resonator as a virtual excitation. So it's a two-step process, and that virtual excitation then gets picked up by the other qubit, so that you can indeed change. You have the flip-flop interaction that changes the position of the excitation among the two transmons. Excellent. The second kind of interaction is what you had in mind. Great. Other questions? All right. Good. On the next slide, oh, it looks like somehow my step-by-step animation is broken on that slide, but we'll deal with that. Okay. So we'll ignore this from this review for a moment. Here's again the Hamiltonian we want to deal with now. And my claim is that it's not exactly solvable anymore. And maybe it's good to just say a few words about that, and I do need an empty page for that. So what I didn't mention, I could have mentioned it for the Jaynes-Cummings model, is that if that's very thick. If I were to write down the Jaynes-Cummings Hamiltonian as a matrix in our basis of bare states, right? 0G, 1G, 0E, and so on, then this matrix, due to this nice property of the total excitation number being conserved, has a very simple form. It has a 1-by-1 block up there. That's the ground state, which was an eigenstate by itself. And then we get 2-by-2 blocks along the diagonal. Right, so this is 1-by-1, and this is 2-by-2, 2-by-2. Right, this is the ground state. This here is the one excitation subspace, and so on. And those were indeed the 2-by-2 matrices that we wrote down and said that it's good practice to try whether you can diagonalize them, right? And they were all similar in form, so we didn't have to diagonalize an infinite number of different kinds of 2-by-2 matrices. That might be bad as well, because this, of course, continues down there. Okay, so that was Jaynes-Cummings, and now my claim is for the system of transmon, even in this approximation, and our oscillator, things are not quite as nice. And that has to do with the fact that, so these, there's still a conservation of the total excitation number, right? So you can check that this quantity, which I'll now write as A dagger A plus B dagger B, this is still conserved, no problem. But those subspaces get larger and larger and larger, right? So it starts out again with a simple 1x1 block. And then the next one, I think, is still 2x2. But then how many states are there where n is 3? Now that I don't have a qubit and an oscillator, but I have two multi-level systems, right? I can do, what can I do? I can do 1 and 2, that's 3. I can do 2 and 1, and maybe this is still just 2. Give me one moment. I thought about this morning, but I admit that I got up at a time that wasn't quite compatible with clear thinking. So am I wrong about this? Am I wrong about this? 1, 2. Maybe the next one is the next one causing problems? If any of you is thinking straight because it's afternoon in Europe or wherever you are, you can pitch in. So maybe the 4 guy is going to help me out here. So I can do 1, 3, I can do 2, 2, I can do 3, 1. So that now is finally growing, right? That looks better. And so my claim is indeed that these blocks are going to get larger in size. And that means that we don't get away with diagonalizing 2x2 matrices, right? These blocks become larger and larger and larger. And in fact, exactly diagonalizing matrices of size larger than 3x3 is only possible if they have a very simple structure. And that might not be the case here. All right, so we have to basically settle for a perturbative approach, and that's all right because we're mostly interested in the small coupling limit in the dispersive regime. And I thought I had gotten rid of all my sign errors, but there's still one on the slide. So strategy number 1 is rinse and repeat. Well, repeat something that I didn't demonstrate, right? We didn't go through all the tedious commutators that one would have to calculate to actually perform the Schrieffer-Wolff transformation. Those commutators don't become much nicer if we do this for the transpon and the oscillator, but it can be done. So that is option number 1. And then this was where my animation was broken. Then I was very excited, and I'm still trying to extract some more information from Alexandre. So if you looked at his review, then they advertise an alternative way, which they say down here. They think that this approach is simpler than performing a Schrieffer-Wolff transformation. And so I was excited. I hadn't actually followed this path yet. It's not a difficult path conceptually, and so we'll look at that, and he hopefully later today he will inspire me to understand whether I'm overlooking something, because if we just briefly jump ahead, I want to show you that once all the dust settles, which by the way happens in an appendix, so it tells you that this transformation isn't that easy either, it does say that in this approach they do in the end have to apply a Schrieffer-Wolff transformation. So I was excited about no Schrieffer-Wolff transformation along the way, which always involves nested commutators. But it seems like even in this approach that they deem simpler, you have to do one in the very end. So we'll hear from him perhaps directly whether that's right or not. But let me tell you the story as far as I understand it. So a nice idea that they propose we follow is, look, we have this Hamiltonian. We said that our anharmonicity is small, and if I ignore this term for a moment and just call the rest my linear part of the Hamiltonian, then all I've got is two coupled harmonic oscillators, right? And that I can always solve exactly. There's absolutely no problem. There are different ways to do this. One is to write this out in this funny form where I group creation and annihilation operators in a little vector, and I write another kind of 2x2 matrix over here, right, which has the entries associated with the coefficients. And if I diagonalize this 2x2 matrix, I can determine the normal modes of the two coupled harmonic oscillators, as well as the normal mode frequencies. And our friends, including Alexandre, suggest that, well, if you do it a slightly different way, but which ends up being equivalent, then maybe you can actually perform a rotation on the Hamiltonian itself. And the unitary transformation that does that looks like this. It's an exponential of operators a dagger b minus a b dagger, and this capital lambda again involves this funny arctan, which is a little bit familiar perhaps still from the Jaynes-Cummings example. And so we'll apply that to our linear part of the Hamiltonian, and all it does is it'll rotate the Hamiltonian so that we're aligned with the normal mode axes, so to speak. So the result will look simple, right? We have rotated, and those now refer to our new normal modes, and they have normal mode frequencies of this kind. All right, so that was just the linear part of the Hamiltonian. And now we are left with our anharmonicity term, the one that has the b dagger, bb. Oh, and before we jump there, there was indeed this one note that I wanted to remember to make. Whenever our system is perfectly linear, meaning it's just coupled harmonic oscillators, there can never be an AC Stark shift. Right, so this special term that we observe for the Jaynes-Cummings Hamiltonian that I said is in fact in real life really important for doing dispersive readout of a qubit. If everything is harmonic, there is no such term. And we will see that in a moment again when we look at the full expression for all the terms that appear in our effective Hamiltonian in the dispersive regime. All right. So as I said, the remaining task that is in full beauty in a not super long appendix, but it was shifted into Appendix B in the review. If you're interested, you should go through it, but I'm not going to bother you with all the steps involved. But what you get intermediately is an expression that doesn't look super simple. And in fact, it still involves terms that are not so easy to interpret, and in the sense of we would like to be able to read off eigenenergies, but we have terms here which still convert between A and B excitations. That's this term here. Something interesting of that same sort might also be going on here. Here we actually convert two B excitations into two A excitations. So this is not yet the simple kind of dispersive Hamiltonian that we managed to obtain in the case of Jaynes-Cummings. And so they admit that, and they say, well, we still have to now get rid of those terms, and we know how to do that, but that'll involve a Schrieffer-Wolff transformation. So I asked Alexandre this morning whether the wolf has just dressed up as what's the name in English? I think it's Red Riding Hood, but the wolf still has his teeth. So we'll find out from Alexandre. In any case, whether you follow this approach, whether you choose to do Schrieffer-Wolff from the very beginning on, once all that dust settles, you obtain a Hamiltonian that looks like this. You recognize the first term as describing, if we're dispersive, then this is mostly the resonator with a slightly shifted frequency, perhaps. This is mostly the transmon. And then there are terms here, which we should consider carefully. So number one here is the anemonicity of the transmon, right? That was the one we started from. It's written out here again. It comes with the charging energy EC. That produces the nonlinearity in the spectrum of the transmon as was. But now we also have a term of the same form that belongs to the resonator. So this is also known as a self-Kerr term in quantum optics. It basically says that once you have more than one photon in the cavity, these photons have an effective interaction. They might attract or they might repel depending on the sign, and the sign here turns out to be negative. And we can tell from the expression for this Kerr coefficient K sub A that this nonlinearity is mediated through the interaction between transmon and cavity or resonator, right? Because it involves a factor G over delta to the fourth, right? It's a term of fourth order in our perturbation theory, and so it's significantly smaller than the original anemonicity of the transmon. And then back here, we have the thing that generalizes that represents the AC Stark shift. Remember that in the case of Jane's Cummings, that form was A dagger A sigma Z. Now we don't just have two levels, so the thing that replaces sigma Z turns out to be B dagger B. And in quantum optics, people would refer to this perhaps not, they would not say it's an AC Stark shift. They might refer to this as a cross-Kerr term, right? It's sort of like a density-density interaction, if that's language that you prefer. And the coefficient, our dispersive shift, has this interesting form. So it's not just G squared divided by delta. We shouldn't expect that it's that simple, because remember I said if we just had two harmonic oscillators and no anharmonicity, then there shouldn't be any dispersive shift. And recall the anharmonicity is governed by EC. And indeed, if I set EC to 0, then this dispersive shift vanishes as it should, right? And so this is the dispersive Hamiltonian for our transmon oscillator system. I'm sure that Alexandre will have a lot more to say about it in terms of how do we use it once we pair it with a drive to control the state of the transmon. How do we read out the transmon? I forget how this is precisely split up between Hanhi and him, but you will see this model come back at you in the future. Since I still have time, so this was the place where I wanted to get today, and I was hoping I might be a little bit fast, because that will allow me to have a little intermezzo of talking about circuit quantization, which I feared I would not be able to do, but I think I'll give you a moment to ponder and see whether you have questions. I'll first answer all questions, but if there's time left, then I'll talk a little bit about circuit quantization so that you actually get a flavor of how to do that yourself rather than have somebody let Hamiltonians fall from the sky. No raised hands. Oh yeah, Julia.
Hi again. Thanks for lecture. I'm just curious in general concept. So am I right that dispersive regime is most kind of suitable for experiment and for theory? I see that there are lots of kind of threads which could be used because of maybe it's not only one photon system and I see here's kind of some problem. You could also comment on that, because I missed beginning, so I heard you said something about cavities modes too. So I'm curious in practical way how it works, and kind of different scenarios without any deep details in theory. So just general concept, because as I see, there are really lots of opportunities to do it.
Sure.
So
I can say a little bit about that. That's right. One thing that might worry us is this AC Stark shift that we see back there. If we're not careful, then it might lead to dephasing of the qubit, right? If I have photons enter and exit the resonator randomly, then the qubit frequency, once I group this term again with this guy over there, the qubit frequency will randomly shift, and I would have to fear that I have to deal with pure dephasing. However, the way this game is played experimentally is all of this, your entire chip holding resonator or cavity and transmon is cooled to millikelvin temperatures in a dilution refrigerator. You might wonder why millikelvin is actually the necessary scale, right? Because there are superconductors, and even some of the superconductors that are being used here that don't require millikelvin temperatures, right? Aluminum becomes superconducting at around 2 or 1 Kelvin, right? So I don't need the 10 or 20 millikelvin that a dilution refrigerator gives me. The reason why dilution refrigerator temperatures are important is that we want to eliminate thermal photons in the resonator. We don't want random photons to enter and exit the cavity or resonator, because that would indeed be problematic. And so that is one aspect. So once this A dagger A remains 0 or very close to 0, then the qubit doesn't undergo random frequency shifts, and it lives its happy life, right? So that's one aspect that I could talk about. Another aspect that I could talk about is, and well, there may be a little bit of redundancy because Alexandre is bound to tell you more about that himself, but he'll do it in more detail and carefully. So how would I think about, how would I want to read out the state of the qubit in the 0-1 basis? In that case, I'm going to make good use of this dispersive shift term in the sense that, I'm going to imagine that I've hooked up a microwave generator to my resonator, so I can drive this A mode. I can drive this degree of freedom. I can push photons close to the resonator frequency into the resonator. Maybe I'll measure reflection. Maybe I'll measure transmission. And the interesting thing is that, well, the qubit state determines where the shifted resonator has its resonance, right? And so by basically looking for where does the resonator have its resonance, I can learn what the state of the qubit is. So that is how readout works. And then I can say one more thing, perhaps. So how do gates work? Gates work in the following way. I'm going to hook up the same microwave generator to my cavity, actually. In most schemes with resonators, cavities, and transmons, it's the cavity or the resonator that is directly driven. But I'll drive it not at its own resonance frequency, but at the frequency of the qubit. So there are actually very few real photons that would populate the resonator, but through the interaction between cavity and transmon, the transmon does get to see those photons. They're exactly at the right frequency to, say, transfer it from its ground state to its excited state and perform an X gate on the qubit, for instance. Those are the simple
So-
things. Does that help?
So it's kind of a game of probability. So last thing which you said. So we kind of it's very difficult to turn into regime, kind of resonance regime in experimental way. So am I right with?
Let's see. I didn't fully catch what you meant by a game of probabilities, but I'll answer the last part first. So if you have a flux tunable transmon, it's actually quite simple to use a magnetic field and tune the transmon into resonance with a cavity or a resonator mode. That's something that is oftentimes not required to do quantum computation, quantum information processing. It's something that people have done to do quantum optics experiments using microwaves, but that can be done. So people have observed many times vacuum Rabi splitting between a qubit and the resonator, for instance. And then tell me again more about the game of probability.
You said about photon populations. That's why I catched it from your last sentence. I got the point when dispersive regime, the main point you can read qubit, and so you don't need to be in resonant regime. Yes, this one I got. Thanks.
Oh no! For the readout, you don't go on resonance, right? So this entire Hamiltonian that we're staring at is only valid in the dispersive regime. So the qubit remains on its own, detuned, quite a bit detuned from the resonator, and all that we make use of is this AC Stark shift. That is what helps us infer the state of the qubit.
Yeah, this one I get. I just pointed out about photon numbers in the system. So how people deal with it in terms of decreases of the number and stabilities, and this terms includes population of photons too. So how it affect on the whole system?
Sure, and you mean that in the context of driving, or in the context of
that's why I said about some probabilities, and you said we need to put low temperatures also to mitigate this factor. And maybe my question more abstract. I'm just curious how precise you need to support and save amount of photons in system to be kind of more stable, because naturally you have some decreases of their numbers, and you can be in purely one photon regime for a long time. So that's why I'm curious how these terms connected with real systems. So maybe I'm too difficult in explanation of what I'm struggling with, but I'm also trying to put this theory into real one system, and yeah, that's the problem.
So one comment that perhaps partially addresses one of your concerns is, so yeah, what about probabilities? We could wonder, you know, we are at 10 millikelvin. What is the population of the cavity? What is the expectation value of the number operator given 10 millikelvin, right? And so these cavities and resonators, they're typically fabricated to be in the range of multiple gigahertz. And if you just calculate your Boltzmann factor, you will find that that means that it's we're nowhere close to even a single photon as far as the expectation value concerns. It's a small fraction, right? And so we're pretty safe as far as that is concerned. And as far as driving the qubit goes, you know, when you drive a high Q oscillator outside of the narrow range of its resonance, you basically don't populate it, right? And it's nice that nonetheless, in this perturbative process, that the qubit can still receive such a photon. it virtually goes into the resonator, never leads to real population of the resonator, but it arrives at the qubit, and you can drive the qubit, you can perform gates. That works quite well.
Okay, thanks for nice comment. Yeah, I'm feel more comfortable now with all that. Thanks.
Sounds good. More questions? Okay, well, I have 5 minutes left. 5 minutes is not going to get us through all of circuit quantization, but at least I can give you a little hint as to what's involved. Circuit quantization. And so the goal really is to go from something like this to a Hamiltonian, right? And you might ask yourself, well, how do you actually do this for a mechanical system, right? If I don't just take a harmonic oscillator or a hydrogen atom, you know, what do you actually do? Maybe I have a stiff rotor or some other interesting system. How would you go about analyzing that mechanical system in that case and find the quantum Hamiltonian that describes it? And the typical way, right, is you consider your system and find appropriate generalized coordinates. And with that, I should be able to formulate a Lagrangian, which depends on these coordinates. So, well, for us, maybe they're called phi sub I, right? And so the Lagrangian is going to depend on both the generalized velocities and the coordinates themselves. So no big surprise there. And then the machinery just goes ahead, right? You do a Legendre transform, and you get a classical Hamiltonian, which in our case would be a function of the conjugate momenta, which turned out to be charges. And we still have our coordinates, of course. And then comes the step of quantization. And I may have said this earlier, but that really is the step that actually works the same everywhere, right? We're just going to say that we replace Q sub I by H bar over I d by d phi I, just as you would replace momentum by H bar over I d by dx, right? And that way we obtain our quantum Hamiltonian. And so the one place where we have to think for circuits is not here, right? So when people discuss circuit quantization, it's sort of funny because the work doesn't really go into the quantization step. The work goes into this part, right? If I give you a circuit, how do you write down a Lagrangian for that? And in principle, you know how that works. It's just not so familiar perhaps for circuits, right? So we say that the Lagrangian is given by the sum of all kinetic energies, and we have to subtract the potential energies. I think I had reserved V for voltage, so let me call it U instead. And for our choice of variables, so our coordinates rather, let's call them that. Coordinates are those generalized fluxes, right? They were given as time integrals of voltages. So I can organize my circuit into individual nodes, right? This circuit has two nodes. One is here, one is there. The nodes connect the different circuit elements. And now with those nodes, each node is associated with one variable. So I'll call this phi 1 and I'll call this phi 2. And now I just have to remember the energy expressions for the individual elements, right? So I will find that the inductor can be written as, well, it's phi squared over 2L, where L is the inductance. So I'll have to subtract my two node fluxes. And this looks like a potential energy term, right? It's a term that involves the coordinates themselves. And then, so I have to subtract this. And then for the capacitive term, I'll remember that 1/2 CV squared is one way to write the energy of a capacitor. And so that one, now I'll have to use the derivatives of the phi's. Those give me the voltages. So I'll get 1/2 C phi1 dot minus phi2 dot squared. And that is my Lagrangian. That is the starting point for now cranking the wheel and getting over to a Hamiltonian and quantizing it. And of course, you see that since only the difference of phi1 minus phi2 appears and not the sum, I can actually reduce this to a single variable problem, which is what you would have expected, right? I can rename this and just say this is phi without any index. So the first one would have been phi dot, right? And then we're back to good old harmonic oscillator physics. And even if you include Josephson junctions, the same strategy applies. And the only thing that makes life a little bit more interesting is how to deal with a case where you have a magnetic flux that might penetrate a superconducting loop. And that one, I don't think I'll have time to explain right now, but that can be taken care of. We have to make sure that we take into account fluxoid quantization in superconducting loops, but that's not hard either. So this is sort of the 5-minute version of how does circuit quantization work. And I think now I'm out of time. Is that right? Maybe, no, we started. Oh, I actually have a lot more. I have a lot of time, don't I?
Well, a lot of time, no, but I mean, if you want to go on 5-10 minutes, I don't think.
I forget how this worked. Do I go till 10:30 or to 10:45?
You have until 54, sorry, 45.
45.
But since we interrupted you a couple of times for long questions, if it's 5 minutes more, we will not.
No, but no, I'm not going to go for more than I was given. But I forgot that I have a little bit more time. So if it's all right, then I will just briefly talk about this how to include magnetic flux, and then we can stop for questions.
Sure. You have other 15 minutes.
Excellent. Yeah, I was confused and nobody corrected me. All right. So how do we do this when there's flux? And in fact, so there's sort of a generalized version of Kirchhoff's rule that we have to obey. So if I go around this loop, right, then I actually have to make sure that I include this flux in my sum. So I would say that if this is phi1 and this is phi2, then as I add up generalized flux differences around the loop, this phi external actually has to enter. So I would say that phi1, in this case, let's do the trick that everybody in circuit quantization does as long as it's possible. You always have the power, at least as a theorist, to determine what do you want to call the zero value of your electric potential, right? I'll call that ground, and probably experimentalists will tell me that ground is something complicated and there can be ground loops, and the ground is complicated. But what I have in mind is really just a gauge question of what do I call zero electric potential. And as a theorist, I and well, you all are entitled to make that choice. So this is going to be zero electric potential. So I actually can describe the circuit with just one variable. That's going to be phi. And so now I have to make sure that as I write down my Lagrangian, I include this external flux in the appropriate way. And I'll just tell you how the recipe works. So if we have a circuit like that, like the one over here, that it has a superconducting loop, right? Meaning that there's a part of the circuit, well, that looks like a loop, but what's important is that it's only interrupted by elements of inductive kind. So, right, so this here is a Josephson junction and an inductor. So I would call that a loop, but this, for instance, does not count as a superconducting loop usually because it's open on the right-hand side where the capacitor has its gap, right? So over here, I would not need to worry about a constant magnetic flux because, well, the loop is interrupted. But in the other two cases, I have to worry about it or have to be careful to do things right. And so the nice treatment of this can be found in two places. I think I had this reference earlier listed on one of my slides. So they have a paper in a somewhat obscure journal that I was not familiar with. It sort of has circuits in its title. We can look up the reference in a moment. So there's this is a paper, and then there's also a book chapter that Michel Devoret wrote in a session of the Les Ouches summer school. So Les Ouches lecture notes, and that is certainly how I learned circuit quantization. And so he has this very beautiful recipe that takes flux into account appropriately by, well, the language, I guess, is a little bit borrowed from graph theory. So we would say, all right, let me just make some more interesting circuit here that looks a little bit more complicated, perhaps. Let's, I don't know. Let's do this, and then maybe there's another junction up here. All right, so this is now a circuit that has how many loops in the way that I explained the definition? You can put in your guess into the chat, maybe. Say 1, 2, or 3, or 0. How many loops? Oh, wow. The silence, 3. Interesting. Yeah, I actually realized this is sort of and yeah, there's a question about independent. That's exactly right, and I wasn't particularly clear about that. I think we all agree that this guy over here, that I did not want to count as a loop because it's open, and then the counting becomes interesting, right? Because they're actually fun logical games or sort of little puzzles where you have to count loops. And the question is, if I say 1 and 2, am I done counting, or should I now also count the big one? Depending on how you did it, you should get 2 or 3, and both of those I'll accept as correct. Now, if it's about sort of this independent is an interesting aspect that Henry brought up, right? If I specify what is the external flux in this loop and what is it in that loop, then I'm done, right? There's not a third one that I can specify independently. So I'll call this 2 loops. But whoever said 3, I appreciate that. I wasn't very clear about what I meant when I said counting. Kevin was that. Thank you. All right. And so how do I take care of the presence of these fluxes? Michel says, well, let's do the following. Even though Michel also does experiments, he's certainly happy with us playing theorist and setting some node to ground. So I'll choose this bottom node to be ground. And now, well, let's actually count how many nodes are left. Let's mark them. So there's certainly one node here, and there's one node there. And then that's it, right? I don't think I'm missing anything. This is everything that keeps this circuit connected when placing all the individual circuit elements into between those nodes. Okay, and so now the idea is let's draw this is now, so step one was choose ground. That's all right. Choose ground. And step two is draw a spanning tree using inductive elements. So spanning tree, what does that mean? The spanning tree starts from ground, starting from ground node. Right, so I'll position myself over here. And spanning tree means I have to draw across elements to the other nodes so that I reach every node in a minimal kind of way, right? So for instance, I could choose to go from ground across this inductor, then I've reached that node, and I could choose to go across the other inductor, and I've reached that node. So that would be one spanning tree because I've now reached all the other nodes in the circuit. So this would be one spanning tree. Spanning trees are not unique. Another choice would be interesting. I disabled the touch functionality of my screen, and now I actually don't know how I can I move this to the right? Yes, I can. Another spanning tree. If we look at the circuit to the left, maybe I can show both at the same time. I need to practice one node, huh? All right, we can see a little bit. So I could go across this inductor again from ground. I've reached that node, and then I could decide that I go across the junction to reach that other node. So that would also be a valid spanning tree. Other choice of spanning tree. And then clearly in this game, there are some branches that I've not covered by the spanning tree. This is jumping back and forth like crazy. Some branches I haven't covered, right? Over here, I've missed this and that one. Over here, I've missed that one and that one. And so clearly I have to include them, and those are called the closure branches. So identify closure branches. And the rule is, and to prove that rule, we should go through fluxoid quantization and what it means indeed physically for superconducting loops. But I'll tell you the rule for now in the little time that's left. The rule is associate the external magnetic flux with each closure branch. And so let's do this for this really simple example of the DC squid. That's easy to do. Let's not do that for the complicated circuit above. So, well, there's one node on top. I can reach that node either through the left junction or through the right junction. Accordingly, the other one is going to be the closure branch. So let me choose this path, and then this one over here is the closure branch. And I'm going to label my junction. So I'll call this has junction energy EJ1. This has EJ2. The fact that I'm drawing them as squares actually means that there's a bit of junction capacitance in parallel. So that symbol means that I have this. So indeed, there's also capacitive energy. Don't have to worry about that as far as the flux proofing is concerned. And so if I do that, then so I'm going to skip the kinetic energy, and I'll worry about what are now my two contributions from the Josephson junction. So remember that the energy was minus EJ cosine of the phase difference. So that there's already a minus sign. I have to subtract the potential energy, which turns this into a plus. So I'll have a plus EJ1. And that guy is part of my spanning tree, so I don't include any flux with that. So I'll have the argument of 2 pi over flux quantum times, I'll call the variable up there just phi. And then the second term is from the other junction, so that's EJ2. And this one now has to include the external flux. So I'll have 2 pi over the flux quantum. Oh, why does my screen jump? That's not very convenient. 2 pi over the flux quantum, and then phi minus, and we'll just call this phi external, right? Phi external. All right. And so that is the proper way to include the effect of an external magnetic flux. Just maybe as a last remark, yesterday we briefly touched on the possibility to make a transmon flux tunable, in fact, by using that DC squid circuit, right? For the transmon, I would typically now have a big capacitor hooked up like that. That would be the flux tunable transmon. That makes everything a little bit chaotic here. So let's get rid of that if I could. Doesn't want to, huh? Why not? Really doesn't want to delete it. I don't know why. But the upshot is that now that I have this Lagrangian, you can see that there's going to be a way to use trigonometric addition rules to combine these two cosines, right? Which will be particularly easy if the two EJs are the same. And that will essentially give me a term that looks like this. It's an effective EJ that depends on the external flux. And if I do things right, then there will be a cosine of 2 pi phi naught times phi left, perhaps with a shift that I can take care of and eliminate. All right, I think at this point I've maxed out my time, which is fine, but maybe there are still questions which I would be happy to answer.
Don't worry, you were 1 minute late, so I really appreciate it. So, questions, comments, doubts?
Doubts are always the best. Why can't I delete this? I don't understand. Microsoft has been bugging me for pretty much the entire past quarter, but that's a different story.
I can see your problem. Okay, it seems that you don't have questions. You want to think about it another minute?
No questions, really? You have to have questions. And remember, there are no silly questions.
Oh no, I made them already. So